Let's solve the following problem. We have a rectangular sheet of aluminum, for example, with which we want to make a box. To do this, we will cut out a small piece from the corners that, since we don't know what it measures, we will call it. From this figure we would move on to this other one. And what they ask us is to calculate the value of x so that the volume of this box is maximum, the largest possible.
Bueno.
Well, if the length of this box, of this sheet, is 160 and I remove a little piece here that measures x and the same little piece here that also measures x, it is clear that the box is going to measure 160 minus twox in length. In width, if it measured 100 in this little piece and this other one are the same and measure x, it will measure 100 minus TWX, and it is clear, right, that if I have removed this piece, the part that folds to the height will be. Since what they tell us is that the volume is maximum, the volume of this figure, which is a prism, is the surface of the base times the height. The surface area of the base across a rectangle would be 160 minus twox times 100 minus twox and finally times the height, which is x. Then we have this as a function to optimize. We are going to develop it, and then as always we will apply differential calculus to calculate maximums or minimums. It is clear that in this case I only have one variable, which is x. If I develop this function that only depends on for x, we can directly put here all the expressions raised to a unit, but well, we are going to make it integer. This would be equal to 16,000. I do 8 for the x, 320, 200 would be in 520, I get minus 520x and finally plus 4x squared, and now I multiply by squared would be raised to q. Once I have that expression I derived versus, as it is a polynomial we directly derive the derivative of 16,000x would be 16,000 minus the derivative of 520 times x squared would be the exponent 2 times 520, that is 1040, times the base raised to 1 unit minus, which is x, plus the derivative of 4 of x cubed, which would be the exponent 3 times 4, 12, and x squared. So we have the expression for the first derivative, and now we have to set it equal to 0 to calculate the maximums and minimums. V of x equal to 0. It is, as you see, a second-degree equation, and I am going to tell you directly what the solutions are. We would have two possible solutions. We are going to call one zone, which would give us 66.7, and another we are going to call XTWO, which would give us 20. Just in case, so that you can review the expression that you can review. The expression that would be left would be x equal to 1040 plus minus 560 divided by 24, and this is where these two values come from, or rather. Let's analyze them. This first value, 66.7, although it is a value that effectively fulfills the fact that the first derivative is 0, if we analyze the problem you will see that it cannot be, because then we would be taking away more from the sheet than it looks like. Twice 66.7 would be 120 points, which cannot be. Therefore, this value is not worth it to us. The value that is valid for us is x equal to 20. Let's see by calculating the second derivative. If this value makes the second derivative positive, put it. The second derivative, v second, would be to differentiate this. It would be equal to negative 1040 plus 24, 2 times 12, times x. And now we have to evaluate the second derivative at this point. The second derivative at the point x equal to 20 would be equal to minus 1040 plus 24 times 20, which would be 480. It is clear that this expression is negative, and therefore the point x equal to 20 makes the volume they asked us to be maximum. What is that volume? Well, I would simply have to substitute the value x equal to 20 into this expression, and we would have to calculate it.